Hello, and welcome to my presentation, Handling 100K Consumers with One Topic. I'm Hongjie Zhai, a research engineer at NTT Software Innovation Center. In this presentation, we'll first start by introducing the background about why we need handling 100K consumers with just one topic. It contains a smart city use case as well as its performance requirement. Then we will show some benchmark results of current Pulsar and discuss the bottlenecks. In the next part, we will show our approaches for resolving these bottlenecks as well as the evaluation details. So now let's start from the background. This is the use case of smart city. And in this use case, there usually exist various data sources, and we want to collect the data from these sources and do the analyze across them. For example, here we have cars, cameras, and sensors in the buildings. So for example, if a camera catches any damage of a road, so we can broadcast the information to any car nearby, and this allows us to avoid the traffic congestion. In this case, we provide a topic for each area and supports all the cars in this area are connected to this topic. So as a result, we expect there are more than 100 key cars connecting to one topic for a huge city. And one more fact is that many devices have their own protocols. So we have MQTT here, and also a REST for IoT devices, and even a real-time streaming protocol for cameras. Furthermore, we usually have to store the essential data. So for example, we need to store the key senses from camera for later analyze, or some key events from the IoT devices. And we also have to prepare different storage in this system. So all this leads to a problem. So the data pipeline becomes too complicated with such various storages and protocols. So it's almost impossible to maintain such a huge system. So how about introducing a unified data hub? We say here a broker instead of various storage and the protocols. Suppose we have a big broker which support various protocols. So all the device just need to communicate with one endpoint. So in nowadays, many brokers even come with a storage or tier storage. So any data handled by the broker is also guaranteed to be persisted. So we only need to work with brokers and their topics. This makes the whole system just easy and clean. So to realize this system, which is Pulsar is a basic framework, and Pulsar have a pluggable protocol handler. So it allows us work with multiple protocols with just one block cluster. So now Pulsar have the pluggable protocol handlers for MQTT, Kafka, or many other brokers. So it also have a good loosely coupled design with Bookkeeper. So it allows it's possible to scale out the storage if we need to store more data without changing the number of brokers. And one more reason is that actually Pulsar shows this good performance in both latency and throughput in our benchmark. So we will talk about it later. And the next question is that, does Pulsar match the performance requirement of our use case? We have already discussed in the previous slides, the requirement of a number of consumers is about 100K. So just like the requirement 1. So we need to broadcast the messages to this larger amount of consumers. And in fact, besides this requirement, we also have another requirement. And one is that as many notification just occurs against the data in real time, we need to broadcast them in a short end-to-end latency. So here we set this as 1 second. So, and we say the end-to-end latency by meaning the time from the message being produced by the cloud services and to the time it's received by the car. So actually, it contains one produce phase and one consume phase. Another requirement is showing the requirement 3 is about handling large message from cameras. Currently, most brokers just focus on handling small messages, for example, the event data from microservices within cloud. So they are usually no larger than several hundred kilobytes. So brokers may have performance problems when the message becomes larger and larger. So however, in this presentation, we just focus on the first 2 requirements, which is how to broadcast the messages for 100 consumers within 1 second end-to-end latency. So we did some benchmark on current Pulsar, and here is part of them. This is a general setting of our benchmark. There is only one publisher which sends 10 kilobytes messages per second to one processing topic. In the meantime, a large amount of consumers are subscribing to the same topic. So we adjust the number of consumers from 20K to 100K. And the broker, we use Pulsar 2.10, and the benchmark is performed by OMB, the Open Messaging Benchmark Framework. So here is a benchmark environment. We perform the benchmark on AWS, and both broker and bookkeeper use the i3-4x large instance type. So it have a 10 GB network as well as 2 SSD. So this helps us to avoid the hardware bottleneck, so we can just focus on Pulsar itself. Because of large number of consumers, we split them into several servers. So it's just showing as a client in this figure. First, let's take a look at the overview of the benchmark result. In this table, there are 2 benchmark items. One is the end-to-end latency, and another is the connection time. So we give both average latency and the 99 percentile latency. So, and here, the connection time means the time from starting the connections of all consumer to the end of all connections. So you can see that the Pulsar already works well with 20K consumers. The 99 percentile latency is just 0.66 seconds, and the connection time is about 4 minutes. So both of them are just acceptable in real-world usage. So however, with the increasing of consumer, latency finally exceeds 1 second with 13 consumers, and further become even larger. So here, 4 seconds for 14K consumers. The connection time is also reach 20 minutes for 14K consumers. So this is not enough for our use case. And even for 100K consumers, it failed to establish the connection because it takes too much time. So there is no data shown in this column. And here, we further do some research on the connection time. So this is a approximation of the connection time. The x-axis is the number of consumers, the y-axis is the connection time. So you can see that the connection time is a polynomial curve, and we expect the connection time to reach 8,000 seconds at 100K, so which is about 2.2 hours. And of course, it's usually unacceptable. And here, this is the distribution of connection time for each consumer with 20K case. The x-axis is the time range. So you can say there's we start from 3,000 and end at about 200,000. And the y-axis is the number of consumers which finish the connection within this time range. So you can see here, more than half of the connection finished just in 1 minute, and about 20% connection finished just in 3 seconds. So, but the problem is the long tail. So some consumers even spent more than 200 seconds here. So this greatly affects the total connection time. So I think there must be a task congestion during the connection. For the end-to-end latency, we split the whole process to 6 stages and measure their process time. The first stage is the produce. So it contains the publish of the message from publisher and the network communication and the process of Pulsar protocol. Then the broker internal process contains some message manipulation, transformation, and some other process. Then the message persistence is also the communications. It's almost communications between the broker and the bookkeeper. Now, after the persistence, the broker will receive a update notification from the bookkeeper, and this is the notification stage. Then the broker prepares the message for consuming, and this is a broker internal process. And finally, it will broadcast the messages to all the consumers. So this is the broadcast stage. So as you can see here, message persistence takes about 27%, and the broadcast takes about 33% of the total latency. So we will focus on improving these 2 stages in the following slides. So here is a summary of the benchmark. Pulsar is already good enough for if there are not too many consumers. So we say, for example, here, no more than 20K. But for 100K consumers, it still needed to be improved for both latency and connection time. And especially for the latency, we find the persistent process and the broadcast process takes too much time. So in the following parts, we'll talk about how to improve the latency and both the connection time. So we know there are usually 2 possible approaches for improving the performance. One is scale up and another is scale out. So here we say scale up by mean that we improve the performance of a single broker. And in the meantime, scale out means that we allow multiple brokers to handle one topic in the same time. So one of the possible design of scale out is called shadow topic. It's shown in here. You can say so it was proposed by a Pulsar PMC member called Jason 918. And you can find the details of this proposal in the following issue. But in this presentation, we'll focus on the first one. It's a scale up style. So we will first propose the broadcast specific models for better performance, and then we will improve the task congestion problem. So now let's get down to the detail. First, let's review the subscription models for Pulsar. In fact, many brokers share the similar models, so this contains also holds for many other products. In Pulsar, a topic must have at least one subscription to dispatch the messages. And also, each consumer must be linked to one subscription to receive messages. And there are 4 types of subscriptions now in Pulsar. For exclusive subscription, so you can say it is in the top of the figure. Only one consumer is allowed to link to the subscription. So it means that if this consumer crashes or disconnects, the messages in this subscription will not be processed anymore. And the failover allows more than one consumers, but it only sends messages to one of them. So it just works like exclusive, but when current consumer disconnects, it can switch to the next one to keep the message being processed. And the remaining 2, shared and key share subscription, are both designed to distribute message across multiple consumers. So each consumer will just receive part of the whole messages, and the number of messages will be well balanced across every consumer. So you can say here is a problem. So there is no model designed for sending the same message to multiple consumers. So we say, so the broadcast. So we have to create a subscription for each consumer to realize the broadcast case. So just like in this figure, we use 4 exclusive subscriptions, and each of the subscriptions are connect with one consumer. So this allows us to broadcast the messages to these 4 consumers. So of course, so here we use as an exclusive model, and you can use any other type of subscriptions, and the results don't change. So now let's talk about the problem when using the multiple subscriptions for broadcast. First, let's take a look at how subscription works. So here is a figure describing the general design of subscription. There are 3 parts. So one is the subscription itself, and also another is called cursor, and then there is the dispatcher. The cursor is used for storing the information about how many messages have been processed. So you can think of it just as a message ID or the position of a stream. So this data will also be synced with a meta store. So you can start from the latest position after even broker restarts. And the dispatcher is actually the only functional part of the subscription. So it communicates with the bookkeeper and check if there are any new messages added to the bookkeeper or not. If new messages have been found, it will pull them out and send them to consumers. Of course, you can say here, so because the dispatcher is used to communicate with bookkeeper, so each dispatch has its own connection to the bookkeeper. So there comes a problem. When we create 100 key subscriptions, there will be 100 key connections to the bookkeeper. So the huge number of the connection is clearly a performance bottleneck here. And but we know this is a broadcast task. So all of the subscriptions just check the same thing. So we want to check the messages in the same topics and try to pull out the same information and get the similar positions. And so everything is just similar. So we can say this amount of connections are definitely not necessary. And even for the cursor, because we just send the same thing at the same time, so we don't expect too much difference between these cursors. But usually, we think that one cursor is enough. So here comes our our broadcast subscription. So we designed this broadcast subscription model specialized for handling large number of consumers. So it guarantees the message order for each consumers and also have many same functions from the existing subscription models, so such as the cumulative acknowledgement and so on. So this figure shows the general design of our model. You can see there is only one subscription for multiple consumers. And this means there are only one dispatcher. So only single bookkeeper connection is here allowed for, here it's used for multiple consumers. So this reduces the load of bookkeeper and will help us to reduce the latency. And furthermore, there is only one cursor here. So there is no duplication of metadata. But because consumers maybe fail to receive the message or maybe fail to send the acknowledgement to the subscriptions. So sometimes we need to resend the message just for some consumers. But for the cursor, it only records the positions which is successfully processed by all consumers. So to do the resend process, we need another lightweight virtual cursor for each consumer, so which can record the incremental positions from the cursor. And this design allows us to know how much message are still under sending by comparing the cursor and the information from bookkeeper. So we can keep these unfinished messages in the cache for better performance, and we can delete any finished message from the cache. And furthermore, the virtual cursor has a lightweight design, so it does not contain any other information other than the incremental position. So this is the evaluation of the broadcast subscription. The baseline is evaluated with the shell subscription. So this is the best result between all four original models. And you can say that the 99 percentile end-to-end latency of broadcast subscription is about 6 times faster than the original subscription with 14K consumers. And the connection time is also greatly reduced because we do not need to create so much subscriptions. And even with 100K consumers, so we can say the connection is finished in just about 1 minute. And so this result is really promising for us, but we still require a better 99 percentile end-to-end latency. So the next question for us is that, can we further reduce the latency to make it less than 1 second? So actually, we find another bottleneck during our benchmark. So this is a bit surprising. So it's an ordered executor. So this executor is provided by bookkeeper, and it's an expansion of standard thread pool. It guarantees the tasks with the same key are executed in the same thread. So the code is shown in here. So we can say that if we provide the same ordering key, so the truth thread will always return the same thread. So it helps us to keep the order of the tasks. And for parser, when sending messages, the parser can run these sending jobs with the same key, so it can guarantee the messages are sent in the expected order. And this is widely used in parser. And we found several problems caused by this executor. The first one is that when we split the 100K consumers into different broadcast subscriptions, and the latency does not change too much. But for example, so when we create 4 broadcast subscriptions and each of them contains 25K consumers, and we can expect that so we have better balance between the internal process of subscription itself and also the communication between the bookkeeper. So this better balance will bring us a slightly improvement of latency with. So, however, so there is no effect in our benchmark. So the reason is that a parser uses a topic name as the ordering key. So this means that all the message sending tasks are serialized as a topic level. So however, we know the subscription is independent for each other. So this is not necessary to guarantee the order across all the subscriptions. We just need to keep the message order within one subscription. So the natural solution is to change the K to the subscription name. And this is the first one. And another problem to the second one is more interesting. When tracing the message acknowledgement distribution, we noticed a very large long-tail latency. So averagely, the acknowledgement just finished in about 0.5 seconds, so a half of a second. But the longest one takes up to 7 seconds. So this greatly affect the 99 percentile latency. So we do some research and we check the network and the consumers, but find no problem of them. So this long latency and furthermore, this long latency all can be always reproduced in every benchmark. So finally, we find this problem was caused by the way that parser handled the acknowledgement. As the figure shown here, the parser splits the message sending process to 2 individual tasks. So one is for sending the messages and another is just waiting for the X. So for each message and each consumer, parser will generate these 2 tasks and push them into an ordered executor. As we have talked about, so we have to, for a parser, need to guarantee the order of the messages. So these tasks will always be added to the same thread. But this style is good for many cases, but when we have 100K consumers, it's slightly different. So you can imagine here, when we have 100K consumers, the parser will generate 200K tasks. And all of these tasks will be inserted to just one thread. So there will be a high possibility that other tasks will be inserted between the one send and acknowledgement pair. So just like here, so for the consumer 1, we have a send and act tasks, but between them, there may be the send and act tasks for consumer 2, consumer 3 to the consumer 100K. And for some unfortunate cases, there may be 10,000 tasks between this send and X. So once the message is sent, so the parser firstly run many other tasks, and it spend a very long time until we can do the actual acknowledgement task. So this leads to a really large latency, and finally cause the long tail latency problem. So in fact, we only need the same tasks to be ordered. So you can say that we can just send the message in order, but the acknowledgement can be placed anywhere. So So here, we can just use a random thread instead of the same thread. Of course, there are also many other options. For example, so if the network have a high latency and we want to reduce the time loss between two sends, we can use another thread pool for the acknowledgement and only keep the same task in this thread. And anyway, so this way of the parser handling the acknowledgement to lead to the latency, and so we change them to we change the acknowledgement tasks to a random thread to reduce this problem. And here is a final evaluation. And so you can see the third row is the final results with improved order executor. As we have discussed previously, the problem of order executor impacts the performance with the increasing number of consumers. So for the 100K consumers, we can say that the 99 percentile gets greatly reduced, and it's about 4 times. And also, connection time is reduced by half. Of course, not only to the 100K consumers, and even the 30K consumers, it also works well. So you can say it also improved about 2 times from a simple broadcast subscription. So here, finally, we have the summary. According to the benchmark, parser is already good enough for many use cases. But when you need to handle some special case, so for us, we need to do the broadcast tasks to a large amount of consumers. So it may be a good idea to implement our own subscription model. And this will bring a huge performance improvement. So we implement the broadcast subscription, and we reduce the latency by 6 times and the connection time by 83 times. And also, even the ordering guarantee is important. Using order executor in the right way is also a big point. So one should be careful, especially when there are large amounts of send and acknowledgement tasks. And actually, so it's not only to the number of the consumers. For example, if you want to send large amount of messages in a short time, so it will also generate many tasks. So even in that case, you also have to be careful with the ordered executor. So this is all of my presentation. Thank you.